Hi, so we're going to be looking at some simple harmonic motion problems, and this is where I put in the units for Hooke's law. So in general, Hooke's law is talking about a spring. It's the force from a spring. It's either K times delta X, and so it's the force due to displacing a spring, either compressing or stretching it. So it's weigh in time for the local under 85 kilogram rugby team. The bathroom scale used to assess eligibility can be described by Hooke's law and depressed 0.75 centimeters by its maximum load of 120 kilograms. What is the spring's force constant? Well, so if I have a little scale here and pretend that, there's a little spring here. And so what happens is as I step on it, if I know that it would displace, delta X is 0.75 centimeters, so in meters that's 0.0075 meters. And one kind of force is being applied is, well, if that's what happens when I put in a 120 kilogram block on here. So if I draw the free body diagram of the spring or this block, I would say, well, there's gravity going down, mg, and then the spring force is sort of pushing back up on it, and this would have to be k delta x. Now, once it's depressed, the net force is zero because it's not accelerating in either up or down direction. So we would say that the spring force has to equal gravity. So k delta x is equal to mg, or k is equal to mg over delta x, and that's 120 kilograms times 9.8 divided by 0.0075. And I get 156,800 newtons per meter. Okay, so it's a pretty big spring constant. A player stands on the scales and depresses it by 0.48 centimeters. Is he eligible? Well, so the force that is going to be happening when he depresses it that far is just, k times delta x. I was thinking F equals k delta x. K is 156,800 times 0.0048 meters. I get 752.64 newtons. But the limit is 85 kilograms, so I got to divide this by 9.8 meters per second squared to get to mass, because this is equal to MA, right, or mg. So the M is 76.8 kilograms. And so, yes, he's eligible. Okay, one type of BB gun uses a spring-driven plunger to blow the BB from its barrel. Calculate the force constant of a plunger spring if you must compress it 0.15 meters to drive the 0.505 kilogram plunger to a top speed of 20 meters per second. Okay. So this equation, we're not actually going to use Hooke's law. There's two equations for springs that we deal with. Is we take the work, or the energy in the spring, is 1/2 kx squared. And I might do it for this one. Let's see. Yeah, because what we know at the end is, we know the displacement, but we don't know the force. But what we know is how much speed will come out of it. And so this is more of a conservation of energy part. Because what we know is at the end, after the spring launches it, it will be moving at this. So we'll know that it will have an energy of 1/2 mv squared. And that energy must have come from somewhere. It came from the energy of the spring, or 1/2 kx squared. The 1/2's cancel, and I can solve for x. X squared would be mv squared over k. No, actually, what do they want? They want the force constant, the spring constant. So they want a k. So k is just equal to mv squared over x squared. And mass is 0.05 kilograms. The velocity is going at meters per second squared, and then the distance is 0.15 meters squared. I get 889 newtons per meter. And so what is the force must be exerted to compress the spring? Well, here's where we use Hooke's laws, because the force has to be k times delta x. And so the spring constant 889, and the delta x was 0.15 meters. I get 133 newtons. Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.